Okay, we have this 6.10, the last question of the shear force bending moment. First of all, you have to draw the free body diagram. Okay, you are going to have two reaction forces at the pivot points at B and also at E. Okay, so we have to solve these two unknowns as usual. Sum of forces in the y direction is 0. Okay, so the only two positive forces you can assume upward to be positive is RB and RE. The rest are all downwards, which is negative. Okay, minus 20 minus 30 minus 3 times 20. Okay, equals to 0. So RB plus RE is 110. Okay, then we take moments about either of the two pivot points. So I would take about B. Okay, one direction is positive, the other direction will be negative. So let's take anti-clockwise be positive, 20 times 3. Okay, RE would be also be positive. RE times the moment arm, the distance is 6. Okay, and 30 will be negative. Okay, minus 30 times 7 meters away. Okay, the UDL will be represented by one single point load, okay, of which the total is 3 times 20, okay, acting at the center of the UDL, which is this location. Okay, how far away is it from B? Okay, this distance will be 2.5 meters. All right, so and it is negative, so it is negative. 20 times 3 is the force, 2.5 is the distance. Okay, so yeah, so from here I will be able to get RE is 50. Okay, and from equation 1 I can substitute and get RB to be 60. Alright, from here then we can draw the shear force diagram. So 20, 40, so it's about here. It will start with a negative shear of downward 20, so minus 20. Okay, and it will remain constant from A to B. Okay, by the time I reach B, I will be pushed up by RB, which is 60. So my new point is then minus 20 plus 60, which is 40. Okay, during the exam, you are supposed to draw to scale. Okay, please take note of this. The force, there's a scaling which will be provided, which will usually be provided. You keep a lookout. Okay, from B to C, it remains constant. Okay, so C to D, okay, it will be gradually pushed down. Okay, so as you go towards D, you will get pushed more and more because the UDL that is affecting you on the left hand side is higher and higher. So by the time you reach D, right, you will have experienced a total downward of 20 times 3, okay, which is minus 60. So 40 minus 60, I'm back to minus 20 again. Okay, so I will gradually go down. D to E, okay, there's no other forces, it will remain at minus 20. Upward force RE at here, so to minus 20 plus 50 will be 30. Okay, so 30 is here and it will stay constant. I reach the end, it will get pushed back down 30 until it reaches 0. Okay, so this is your shear force diagram. All right, and as we look at the bending moment, it's going, okay, so first of all, we know that the beam, okay, is at both ends free end, so both ends will be 0 bending moment. Okay, so it's going to start from 0 and end at 0. Okay, and like I always say, the gradient of the bending moment line is the value of the shear force. Okay, so from A to B it's going to be a constant gradient of -20. So you have a line that's going downwards with a gradient of -20. Okay, so if I go gradient -20 and I go for 3 meters, -20, -40, -60. So I will end up at -60. Okay, like this. So this value will be -60. Okay, and also at the end, I'm supposed to climb up with a positive slope of +30 across 1 meter. Okay, across 1 meter. So in order for it to climb up and reach 0, it should start from the bottom, right? So I'll climb up over 1 meter of gradient 30. Then so this value should be 30, -30. Okay. So we have the head and tail pretty much covered. Okay, in fact we can do 2 more, which is these 2 straight lines, because you can also estimate how much they climb. You see, this part B to C is going to be a positive slope because the gradient is +40. Okay, so if my gradient is +40 across 1 meter, I will have climbed by 40. Okay, so my new point now is -60 plus 40 will be -20 lor. Okay, so -20. So actually this value is -20. Okay, this value is -60. Okay, so it's going to be here. Likewise, this line here, this gradient is -20. Okay, so this line, this part D to E, the line should be going downwards with a slope of -20. Okay, and as I traverse over 2 meters of -20, I would have dropped by 40, right? -20 -40. So here I would have started from +10, because +10 -10 -30. Okay, the gradient is -20 ma. Okay, so this value here is in fact 10. Okay, it's in fact 10. Yes, so we have one quadratic curve over here. Okay, and this point, this intersection here, 0 shear, is an important point. Okay, because this is where your bending moment will peak. Okay, so peak by how much, we are not so sure yet, but we can find out later lah. So it's going to be it's going to look like this. Okay, it's going to look like this. It's going to look like this. So it's a quadratic equation. Peak here, we don't know. Okay, so our job now is to find this position, this value. Okay, because only after finding this position, then we can find this value. Okay, and then we also have to find the contraflexure point here. Okay, there's another contraflexure point here, which I think it is not so tough to estimate because this is a straight line. This one is a curve, more challenging. Okay, so let's find the 0 shear first. As usual, I will call this distance x. Okay, and this location is x. Okay, and going by, you see, it starts. It is at when it is at C, right? It is at 40 shear force. Okay, how much distance do I need to travel under the constant UDL of 20 for every meter? Okay, how much distance do I need to travel so that this 40 will be negated to become 0? Okay, intuitively the answer should be 2 meters lah. Okay, because after I travel 1 meter, I will drop by 20. I travel another meter, I will then drop to 0. Okay, so the equation is 20 times x equals to 40. Okay, you can also use the similar triangles. Similar triangles, you have to compare this x distance with this distance. Okay, versus this height of 40 with this height of 20. Okay, give it a try. But for now, we are able to find that x is 2 meters. Okay, after we find this, then we can find this value, maximum bending moment. Okay. Let's find this bending moment here. Okay, so we're going to cut the beam at x. We're going to cut the beam at x. So on the let me see. Okay lah, whether you want to look at left or right, it doesn't really matter. We have about the same number of forces. Okay, so let me see. It's 3 meters. RB is 60. Okay, and 2 meters, 3 meters, 2 meters. Okay, we roughly have this much. Okay, A, B, 1 meter. This is 2 meter. Okay, C, and this is X, 2 meter. Okay, and then we have an unknown moment here, 360. Okay, so you take moment about the place where you cut, which is x equals to 0. Okay, so I have m, I have 20. The moment, the distance is 6. Okay, I have 60, which is negative, and I have UDL. UDL will be the UDL is 20, right? So it's 20 times 2 meters, which is 40 kilonewton, acting at the center of the UDL. Okay, so since this is 2 meters, so the distance will be 1 meter. Okay, 20 times 2 times 1 equals to 0. Alright, so my moment is how much? My moment will be 20. Okay, 120 minus 180, which is minus 60 plus 40. Minus 20 shift over, become 20. Okay, kilonewton meters. So I know this moment here is 20. Okay, we've solved this part already. Alright. Determine the position of the contraflexure from A. Okay. So we need to find this place now. Okay. This one, let's say, let's see, are we able to deduce? Because you see, this location is 10, 10. This E is at minus 30. This is across 2 meters, right? So this one should have traveled half a meter. Okay, because the gradient is minus 20. Okay, so if I travel half a meter, I would reduce by 10. Okay, so this distance is 0.5 meters. Okay, so this pretty much solves the last part, one of the position. Okay, and the question is determine the position from A. So 3 plus 1 plus 3 plus half. So it's 7.5 meters away from A. Okay, so for part D, one of the answer is 7.5 meters from A. So it means this point of contraflexure. Okay, now we have to find this point of contraflexure. How do you find? Again, let us mark this distance as y, okay, and I will mark this position as y, and we cut the beam here, okay. So if I cut the beam, 23, RB is 60, okay, 1, and actually I don't know how much is this, but this is B, this is A, this is C, this is Y, okay, and this distance is Y, okay, and UDL is 20. We have a moment here M, okay. So this would be, after you cut, this is the free body diagram. So I will sum moment about M, about Y is equals to 0, okay. The equation will be M plus, let's do the easy one first. Okay, never mind. Let's do the UDL. UDL, the total force will be 20 times Y, okay, and it will act at the midpoint of Y. So 20 times Y is the force, half Y is the moment distance, the moment arm, okay, and same direction as M, so I will put a plus, okay. 60 is opposite, so it's minus 60, and the distance away from Y is 1 plus Y, okay. 20 is same direction as M, so it will be a plus, okay, 20, and the distance from Y is 4 plus Y equals to 0, okay. So this is your equation, which you will need to simplify, okay. And one more point, because this Y location, right, is actually here, okay, and it states that your bending moment here is 0, okay. It means that the M here is 0, so you don't even need to consider this, okay. M here is 0, okay. So we're gonna have 10y squared, okay, minus 60y plus 20y, so it is minus 40y, okay, minus 60 plus 80, so it is plus 20 equals to 0. So your quadratic equation is y squared minus 4y plus 2 equals 0. And you have to use your calculator to find the root lah. So your root is 0.5858 or 3.414, okay. Which one you take, of course you have to go back to this this distance here, and then you see your UDL is not even, is just 3 meters. So how can the distance be 3.414? Okay, so we reject 3.414, and the answer is 0.58. Okay, but the question again is the distance from A, right? So the answer should be 3 plus 1 is 4 lah. 4.5858. Okay, so it's 4.5858 meters from A. Okay, so there you have it. Quite tedious, but the process is very standard.